Thank you very much. Thank you for this nice introduction. I'm looking forward to 45 minutes of Go. In the next 45 minutes, I'm going to talk a little bit about an upcoming feature, which is generics in Go. But before we dive into the content, let me quickly introduce myself. If you are new in a group, I think it is a good manner to introduce oneself, and I would like to do that. So this is me. In this case, you see me live, so I can move it over my picture here. My name is Stropek. And I am broadcasting from beautiful Austria here. I'm living in a small town near Linz, which is called Leonding, and here I'm an entrepreneur. I have a small company which is called Software Architects, and we are primarily working in the cloud business. So what we do is we help small, medium, and large companies be successful in the cloud. And additionally, we also write our own software as a service products, which we publish or have been publishing for more than 10 years now. We founded our company with the explicit purpose of working in the cloud. So we are, let's say, born in the cloud, something like this. So cloud computing, public cloud is what I do, what we have been doing for the last 10 years. So let's continue here. If we talk about DevOps, and we are here on the DevOpsCon, then I am a little bit more on the dev side than on the ops side. But nowadays, as we all know, dev and ops come together, and therefore there is no real distinction here. But I am a passionate programmer for more than 25 years, and the topic of operating real systems came to me in the last 10 years when we started to really embrace the idea of cloud computing, and DevOps. I work a lot with Microsoft, so I consider myself a specialist in the Microsoft Azure cloud. I'm a most valuable professional for developer technologies in Azure, and also a Microsoft regional director. But don't get me wrong, I am not on the payroll of Microsoft, not at all. I do not even have shares of Microsoft. I'm independent, but these are titles that you typically get when you do a lot of work in this area. Beside my typical work, I work also as a teacher and as a mentor because I do a lot of work with the community. I'm chair at the Coding Club Linz, and we run Austria's largest programming club for kids. And also we founded a Rust meetup. So as a passionate developer, I'm passionate about a lot of programming languages, not just Go, which is today's main topic, but I also do a lot of Rust thing. So that's essentially me, and if you want to stay in contact after this talk, use the link reinestropek.me. It's my digital business card, and you can find links there with links to LinkedIn and Twitter and Facebook and YouTube and GitHub and so on. And if you like, just link yourselves up with me, and if you have any questions after my talk, feel free to get in contact, get in touch with me through these social media platforms. Enough with the introduction. Without any further ado, let's dive right into the topic. I would like to start my presentation with discussing the current situation as it is in Go. You know, I know a lot of programming languages. I do work in C#, in TypeScript, in Rust, in Go, in JavaScript, and a lot of these languages. And one thing is really typical in all these languages. They support generics. Generics are important, but in Go, there are no generics. Go is a very simple language, as you probably know. You have probably heard about Go, otherwise you wouldn't be in this talk. So you know that Go is a kind of, let's call it, programming detox. It's a very simple language. It's a language that develops rather slowly compared to platforms like JavaScript, for instance, or Rust. And therefore, the Go designers at the very beginning said, generics make the language unnecessarily complex. We do not absolutely need generics. And to be honest, Go came pretty far without having generics. But still, there are situations in which you would like to build generic data structures or generic functionalities, like handling lists or graphs and things like that. And that is kind of hard in Go. Nowadays, you have two popular options. You can, on the one hand side, rely on code generation. Here are some links to popular approaches in that area. Or, and that is done in many cases, even in the standard library of Go, you use the so-called MT interface. It's interface curly braces. One example is Go's element type in the double linked list. You can click on this link and you will see that the double linked list in Go standard library is, for instance, defined as just an element, and an element is nothing else than the empty interface. For those of you who are not that deep into Go, let me quickly recap what empty interface means. Go relies on something which is sometimes referred to as duck typing. If it walks like a duck, if it sounds like a duck, let's consider it a duck, or more formally speaking, it's structural subtyping. So a type, like a structure, implements an interface, or is compatible with an interface if it implements all the functions which are contained in this interface. So as soon as you have all the capabilities, all the functions inside of your structure, you are compatible with this interface. And if you have an interface without any members, then you definitely always are compatible with this interface. That's the whole point. And this is what the empty interface is all about. Let's quickly take a look at a short example from the standard library from the containers list here. Check out this one. In line 14, I'm allocating a new list. And in line 16, I am defining a variable which is called value, and note the type here. The type is the empty interface. So I'm not saying anything about the concrete type here inside of value. And therefore, I can then assign a string to value, I can assign a number to value, and I can assign a structure to value. All of these things implement all the functions of the empty interface, because there are no functions and it's not really difficult to implement the empty interface. So therefore, it's perfectly fine to push all these values into a list, and we can do whatever we want. But this has drawbacks. This has a few problems. Let me make my video a little bit smaller here so you can properly see the slides here. The problem with interface is we frequently need runtime type assertions. Here is an example what I mean with that. Please take a look at this hero structure. This hero structure consists of two fields, name and can fly. It's not relevant here. And here you see in line 16 that I'm allocating a new instance of the hero structure, and I'm assigning it to a variable which I explicitly typed as being of empty interface. So in line 17, I have to check with Go's type assertion functionality. I have to check if I want to know whether something is compatible with whether something is a hero, and only then I can do something with it. I can also implement an additional interface for the hero structure. In this case, as you can see here, I'm adding the string function, which leads to me, hero, implementing the format stringer interface. And then I can, for instance, as you can see here, use type assertion to find out whether something implements the stringer interface or is compatible with the stringer interface, and then I can call the string function as shown here. So that is a kind of problem with runtime type assertions. Of course, a lot of things can go wrong in that area. Now, generics would be a useful extension to Go, because there are many situations where generics make these runtime type assertions go away. That makes your code more robust. It makes the code type safe. The compiler can tell you if you screwed something up, and also you have fewer runtime errors. So that is a big advantage and makes developers generally happier. Where are we with generics in terms of Go? The generics are an accepted proposal, and the development is good underway. Generics will land in Go 1.18, and Go 1.18 is currently scheduled for early 2022. So we are just a few months away until you can use the features that I'm going to show you in the upcoming 30 minutes or something like this. So here we are. In the upcoming 30 minutes or something like this, you can use them in a few months. Good. So let's go on. Let's talk about generics. And I'm going to talk first about type parameters. Type parameters are a new concept in Go. I just read that somebody asked me, you want to have a larger code window. Fully understand that. I will use the zooming tool to zoom in the upcoming code samples. If you can't read something, please let me know via the chat window, and I will try to do my very best to increase the size of the code window. Okay? Good. Let's talk about type parameters. I will zoom in a little bit, as you can see it here, so that you can see the code a little bit better. I have to zoom out a little bit in order to show you the animations. Oh, I don't. In fact, I can do something like this, and I think it should work now. Let's see whether it works. So this is a typical example for what will be possible in Go with generics. Here you see the type parameter. Let's go back one step. In line 6, you see a function which is called print. And this function, print, should print all the elements of a given slice to stand it out. The code is pretty straightforward, but the point is we want to print anything and we don't want to use the empty interface. So we can use a type parameter. In this case, the type parameter isn't super useful because it just says any, and any is something new. Any stands for the empty interface. It's a kind of syntactic sugar. It's a constraint, technically speaking, covering any type. So you can pass in anything. It's not super useful with generics, of course. We want to constrain the types more, as you will see in the upcoming minutes. Just give me a second. It will become more useful, but this is the basic syntax. So you use the square brackets after the function name, and there you can define the type parameters. After the round brackets, you can define the usual parameters that you are used to. If you want to use such a generic function, you simply call it by specifying the type parameter just as you would specify the usual parameters. So you see that one, and if you don't want to specify the type parameter, that's possible too. This feature is called type inference, and in this case, Go figures out automatically what the type is. Oops, sorry, I have to go back. So let me zoom out here again and show you what I mean. Here you see that we are passing in an integer array. And up here, you see that the second parameter, the parameter is the generic type t, the type parameter t. So Go figures out automatically that t, in this case, has to be int. We do no longer have to specify the integer parameter here. Okay? So that is the idea of having these generic types and type inference and so on. So I hope the code is possible to read, and it was fine if I zoom in a little bit. So yeah, I see, thank you, and it seems that it is good now. Okay, that is nice. If you can't read the code, by the way, I already sent you the link of the slides. So maybe if you have two video monitors, you can open up the link of my slides. You will find all the code there. Then you have it in beautiful full resolution on your second monitor, and you can watch me on the first one. So I hope that helps. Okay. Of course, we are not bound to a single parameter. We can specify multiple parameters for our functions. And in this case, I would like to draw your attention to the map function. Let's quickly inspect what the map function does. Let's go back one step so you see it properly here. The map function takes in a collection, a slice of items, and you see the generic type parameter t1 here. And then I'm using a function parameter as the second parameter. It's called mapfunc. And this mapfunc is the mapping function which translates or projects T1 into T2. And what we essentially do in the implementation is we call the map function for each element in items and return the resulting slice from our method. So this is the reason why in this case we have two different type parameters. So obviously no problem, and yes, you can again use the any constraint, and you will see other constraints in a second. Okay. Oh, I just see that my zooming doesn't really work, does it? Okay, I hope you can read the slides. So I will go out again and let me try something. If I zoom in this way, typically it really works, but I want you to be able to read the slides, so let me give that a second. It will just take a second, and I check the control monitor how this works. Let's see. Yes, okay, I have to zoom in this way. Okay, there is a technical glitch here on my computer with my zooming tool, but now I know how I can zoom, so I can really give you the best impression that you can get from my code. Okay, so multiple type parameters. Okay, if you take a look how the type parameters are resolved, you see it here. You see that in this case the map function gets a slice of integers, and therefore because it is a slice of integer, it is mapped to t1. So t1 is definitely an integer, and you do not have to specify the type parameter, just as we've seen before. And Go is also pretty smart when it comes to type inference, because if you take a look at the mapping function, t2 is automatically inferred from the return value of the mapping function, which is specified as the second parameter to the call to the method map. So Go is pretty smart here. However, Go is not as smart as other programming languages could be. Because it could automatically figure out, let me zoom in again, it could automatically figure out that the result of this expression here is of type Boolean, and therefore it wouldn't, strictly speaking, be necessary to specify bool here. Other programming languages, like for instance C# or Rust, can do that, but this is a limitation in Go. This does not work. You have to specify bool. It's not a difficult, not a problematic thing here, but it is like it is. Go has to be simple, and therefore, yeah, it works like it works. Yeah. Okay, so multiple type parameters and type inference with more complex types like a callback function. Next one. Type parameters and channels. So let's put my video here and let's take a look at this code here. Good. Zoom in so you can see the code really well here. Please check out this code. Again, I'm using a function. This function is called concat, and the implementation is not really important here. So don't take a look at the grayed out code. That's not super interesting here. We just want to take a look at the method signature in this case. The concat function here in Go accepts a type parameter t. Again, we are using any here, but take a look at the parameter types. The C1 and C2 are channels of T. Yes, you can use generic type parameters for channels, and we are also returning a channel of T. You can, of course, guess from the context what this method does. It's called concat because it concatenates two channels. It takes the values from channel 1 and then takes the channels of channel 2 and concatenates two channels and create a result channel in a separate Go routine. So you see in line 6 I'm creating a channel of the generic type, and then I can easily run a Go routine and return the resulting channel based on a generic type. So it's absolutely no problem to use generic typings with channels. Now let's take a look how we can use that one. Let's move the video here so you can see it properly. And let me, yeah, I need to keep it that way. I hope you can read it. Please take a look at the main method. And as you can see, we are using the concat method in line 15. And the C1 is essentially in line 2, declared in line 2. And here we make a channel of string. And by creating that channel of string, Go can infer the type of T from the concat method. So it takes a look at the type of the channel when the variable is created, which is the first parameter to concat. And from that, we do not specify the type in the call of concat, but it is inferred from the parameter, from the variable declaration, taken from there and injected into the call as expected. So this is an important one. So no surprises here. Generics work with channels. It would be a shame if they wouldn't, and it's a good news that they do. Last but not least, again, let me zoom in, I would like to point out that you can also specify generic type parameters when you use type definitions like function types. Let's take a look at the first one. Here we define a function which takes any item of type t and returns a boolean. This is frequently used when, for instance, using some iterators where you would like to filter on a collection of things, on a slice of things, for instance, and you would like to filter all the items which do not adhere to a certain predicate, to a certain filter condition. So the generic function type for this kind of filter condition would be written like that. You define a type. This type is called predicate. The type gets a type parameter t, and then you can use the type parameter t in the declaration of the function. If you take a look at the second one, it's very similar. It's an iterator function. We will use it later on in an example. And this iterator function again has a type parameter t, and it says this iterator function is a function that returns a reference to type t. Why we need that? If you are curious on that, you are in the right session, because we will talk about that in a few minutes. Okay, so these were some basics about type parameters. So we can go next level, and the next level are type constraints. So far, we have always used the any constraint. So essentially, no big advantage compared to the empty interface, right? A little bit, but still not a lot. Type constraints make this thing much more interesting. Let's take a look at this example. I will zoom in a second here. So let's go here. I will go back here, and now it is good. Yes, this is good. Let's talk a little bit about the code that I have written here. We start by taking a look at the hero structure. We had it before, and then I implement, as you can see here, the format stringer interface. You probably know it. The format stringer interface enables a structure to be turned into a string. Then I define an interface. Here you see it. And this interface is called joiner. It takes an existing string and adds something which implements the stringer interface. Very simple interface. Last but not least, let's zoom in here. Here it is. Last but not least, we see that I implemented one implementation of the joiner interface. I called it comma joiner, and it does what the name suggests. It uses comma to separate the strings. This is for demonstration purposes only, so this is a rather naive implementation. You can definitely make it better if you want to have production line code, but this is not a training or workshop about Go. It's really, I want to focus on generics. But you might say, hey, Rainer, no generics here. Why do you show us this code? Well, the interesting stuff comes here on the right-hand side. This is the generic code. And now let's take a look at the join function. I would like to draw your attention here on this generic type parameter. This generic type parameter for the method join is now no longer any. We are using a type constraint here. Okay, let's write it here, type constraint. We are saying, hey, Go, the join method works for all types S, but they have to implement the interface stringer. So you see, we can restrict the types which can be passed in as a type parameter, meaning we can restrict the types on which join works. So if we take a look down here I'm calling the join method and I'm passing in heroes, and we now know that heroes is perfectly fine because heroes implements the stringer interface, and therefore I can pass it in as a parameter to the join method. Again, recognize, let's take a different color, that we are not specifying any kind of type explicitly here. This is done automatically. Type inference at its best. Go figures out the type automatically and makes sure that your code is type safe. Now, once we have the stringer interface, we can easily call the join method, as you can see it here. And if you remember the join method from the top of your head, we had it before. The join method only accepts an item which fulfills the stringer interface. Is that the case? Well, the item is here used in a for range loop. The range loop comes from here. The items are of type S. It's a slice of S, and S is again the stringer, so Go can definitely say this is okay. This code works. This code is consistent. And this is how type inference works with type constraints. Another thing that I want you to explicitly note here is that the Go designers decided to use interfaces as type constraints. And that is somewhat different from other programming languages. If you take a look at C# or Rust, for instance, there you have different constructs where you do not need to use, for instance, interfaces as type constraints. You can use a lot of other things too when doing type constraints. But in Go, you use interfaces, collections of functions, as type constraints. So I hope this example was easy to follow, and by zooming in a little bit, you could see the code properly. So you can take a look at the things, at my beautiful arrows here that I've drawn, but yeah, I will zoom in so you see it better. Okay, next one, next level. Sometimes it's really useful to be able to specify that a certain a type constraint is based on existing base types, and that is particularly interesting when using operators. Let me show you the aggregate function before we take a look at the type constraint shown above. The aggregate function in this case takes a type parameter t, and I would like to draw your attention on the adder type constraint here. The adder type constraint says, hey, I want to be able to add, here you see the add functionality, to use the plus operator for adding things so I can calculate a result. So I specify a seed value and then I use the plus operator to add two elements. Now, as you probably know, in Go, in interfaces, I cannot add operators. They are not supported in interfaces. I cannot tell Go that a certain interface has to have the capability to support the plus operator. This would be possible in C#, for instance. It would be possible in Rust, but it is not possible in Go. But still, for a lot of types, Go knows that the plus operator is defined, and therefore we can use so-called type lists. So whenever you define an interface which should be used in conjunction with generic types, you can specify a type list as shown here. The tilde here at the beginning, this one, just says you can accept exactly that type or any type that has this type as its underlying type. So if I define my own string type, which is backed by a string, it's also perfectly fine to use it for the adder interface. This is the tilde here at the beginning. Of course, you can leave it out and then you explicitly say string and only string. Even if I have a type which is just based on string, it's not usable. Only the predefined data type string would be allowed. So if you remove the tilde here, just a string. Otherwise, any string and any type that has the underlying type string or unsigned integer or whatever you want to have. So therefore, this works properly fine. Here, the OR operators are simply a concatenation. So I'm just telling the system that all these base data types, all these built-in data types are fine. And then Go can automatically find out that it is okay to use the plus operator here because the plus operator is defined for all these types in the type list. Now check out how we use this. I will zoom in again. Here I'm defining a type which is backed by unsigned integer. Now you know why it was important to use this syntax here inside of our type list, because in this case I'm using the index type and not the uint type directly. So if I specify aggregate and specifying the index, it's perfectly fine. It's also fine to use the integer directly, and it's also fine to use the string data type everything works fine because the plus operator is defined on all these types. These are type lists. Typesets, sorry, type lists was the old name. Typesets. These typesets can be specified in the interface, and of course the interface can additionally contain some functions which also have to be present in order for a type to implement the adder interface. That's completely up to you. You can add whatever you need to have in these interfaces. So here you see some arrows drawn in. Okay, some comments. Again, I repeated, interfaces can have typesets and methods. Both are possible. The typesets are only relevant when you use the interface in the context of type parameters. There are two new pre-declared names here. One is called any, we already had it, and the other one is called comparable. Oh, I forgot a closing bracket here, sorry. No compiler checking my slides, I'm sorry. Comparable is kind of special because comparable is also defined for interfaces and instances of structs and so on, and therefore it's not possible to put it or to cover it with the usual typesets. So Go knows an additional new pre-declared name which is called comparable, and that supports all the types which support equal, equal, and not equal. In the future, there might be a constraints package with additional frequently used standard constraints, but this has not been finalized. This has not been fixed yet. Okay. Good. Next level, generic types. I just will take a sip of water and check whether we have any questions. Daniel asks a good question. What is the argument for adding any when it is just the interface, the empty interface? Just to make it shorter, exactly that. Any is not a generically usable abbreviation of the empty interface, so you still have to use the empty interface if you want to express exactly that. Any can just be used for a type constraint in a type parameter. So it can only be used in the context of type parameters. And it just makes type parameters look a little bit nicer. That's all. You can discuss whether any is useful or not. I linked the specification and you can take a look at the GitHub repository, and this is heavily discussed, but at the end of the day, any made it there, and I think the syntax is pretty nice and pretty good to read. Okay, generic types. We have a little bit more than 10 minutes left. That's perfectly fine. So let me show you that one. The big difference here in this example, let me zoom in here. The big difference in this example is that we now here use generic type parameters for a type, for a struct. So now we are no longer using it for a function, but we use it for a structure. Of course, we can then add some methods like creating a new vector, as you can see it here, and adding two vectors, for instance, and take a look at the vector element type here. See that one? This is another example of, can you remember the name? Yeah. Here you see again this list of types, this type set, where you can define that a vector can be of type integer, unsigned integer, float32, and float64. That's the idea here. So we have a type constraint with a type set and a structure which is a generic structure. Now let's take a look how we can use this one. We can simply say create the vector and specify the values here, 10 and 10. As you can see it here, this 10 will relate to this parameter. This parameter here goes here to this parameter. This vector element has been defined up here, and the vector element contained the integer, so therefore it's perfectly fine to use the integer here. So the Go compiler really follows the traces back to your type constraints to make sure that everything is consistent. And then we can add the vectors, as you can see. The important thing here, and please note that, is that we are using the same type parameter here and here, so we can only add vectors of the same type. So we cannot simply do anything else, but we use the same type parameter here, and therefore we can easily add the two vectors and get the expected result. So this is how you can create generic structures. Okay, so put here. I already specified that. I told you that. Oh, that's fine. There is a limitation, however. The limitation is that there are no generic interfaces. As a developer coming from languages like TypeScript or C# or Rust, that was kind of a surprise for me, because all these other languages, they support generic interfaces, but generic interfaces are not supported in Go. And if you are interested in the details, please take a look at the proposal and the history of the proposal. But to make a long story short, you cannot define a generic interface. Okay, that's simply the case. Good. So I have one last thing for the final, let's say a little bit more than 5 minutes, and then we have a little bit of time for Q&A. Let's have some fun with some generic functions. I came up with a non-trivial example where we can practice and take a look at more advanced things that you can do with generics. I wanted to play a little bit around with generators and iterators and functional programming and so on. And let's take the last 5 minutes as a kind of summary, but not by theoretically repeating all the things that I said, but let's take a look at an example to make really sure that everybody understood the concept of the generics here. It's not super complicated, so it should be fine for everybody. So let's take a look at first on these three functions here. The first one is not a function. I want to draw your attention to here. It is a function type. So we have a category of functions which are called iterator functions, and essentially an iterator function is a function that returns a reference to something. Okay, that is defined here. Why this is useful? Be patient for another few minutes. You will get it in a second. Then we define a generic iteration function. Let's call it the next function, and this next function gets a generic type argument, which is t, and in this case next receives an iterator function, so the function which at the end does the progression to the next element is passed in as a generic function here in the first argument, and all this that the next function does, it's calling the iterator function. Why this is useful? You will see it in a second when we look at the for each function. Now the for each function is a typical iterator function. We can specify that the for each function gets an iterator function, as you can see it here, and gets a function on the same type parameter. Please note the type parameter here. That should be executed on every element of the iterator. So what we do is we call the next function first. This is this one. So we get the first element. Then we iterate until we reach nil. And in every loop iteration, we call the next method. And inside of this loop, we simply call the body method, as you can see it here. So this is a different kind of programming style. You see it pretty frequently, these iterator styles. If you like it or not, I'm not sure. Maybe it will influence your programming style a little bit when we get the generators, the generics. But for practicing and understanding the generic type parameters, I think this example is pretty awesome. So let's take a look how we can use this. We can, for instance, define, as you can see it here, a numbers iterator. This numbers iterator generates a sequence of numbers, and in this case we are doing that by returning a function, a closure to be more exact, a closure which is based on the current value, which is incremented whenever we call the function. So we return the iterator function of int because we are generating int values, and with that we can easily call the for each method here with the numbers iterator and apply this function. In this case it's just a print function on all the elements of the iterator. Again, I am perfectly aware that you can and you probably might implement this today differently, but in many other programming languages, including Rust, C++, C#, and so on, this is a very typical and very frequently used pattern where you use, in this case, a generator to generate values and a generic iterator to iterate over these things and apply a certain function on it. And here you see the power of the generic elements, because here we define the generic type parameter int, and this generic type parameter int drives the rest of the type checking. This int goes here, from here it goes to the next. The for each has a type parameter. You do not here specify any type parameters at all. You just use here the integer value. You get the generator with the integer values, and then everything else is done automatically. So type inference is pretty powerful, as you can see it here. Now let's do something which is a little bit more elaborate and a little bit more useful. So you can take a look at the code afterwards. Let's, for instance, add a filter functionality based on our generic generator and iterator here. What you see here is I'm specifying here a new kind of function. I call it the predicate. You have seen it before, now we use it. A predicate is any kind of function which receives an element t and returns Boolean. And we can use this guy here to implement a filter iteration function. Again, we are using our generic, note that we are using the generic iterator function and the generic predicate function type. So we get a function doing the generation or iteration, and we get the predicate which does the filtering. And then again, we are creating a closure over an anonymous function and our iterator, as you can see it here, and we are simply looping over the iterator. And we are, as you can see it here, we are simply going through the elements. Sorry, I cannot zoom in properly. We are going through all the elements and we are ignoring all elements, here I can zoom in, which do not result in true, but which result in false. We just skip them, and the first element, which is now fulfilling our predicate, is returned. And because this is a closure, and we are using the same iterator here, the iterator is incremented, and when we go back into the next iteration of filter, we get the same iterator, and we use the iteration from the point where we left. So using this kind of programming style would be a for each, which is wrapped around a filter, which is wrapped around a generator. We can specify an anonymous function for doing the filtering. We want to return only the even numbers here, and then the for each method is just printing the result on the screen. So you can do something like this, and as you can see here, when using these functions, we do not specify any type parameters at all. Everything is solved with type inference. And last but not least, we can take this one step further, and we can, for instance, define a function which generates an iterator function, again generic, from a slice of t, where we simply again create a closure over an anonymous function and our items. We return the item from the slice, and we create a new slice where the first element is cut. And with that, we can, for instance, use our iteration function, as you can see it here, based on a slice of a structure. So we turn a slice into an iterator, and then we can apply filtering, and we can apply for eaching, and a lot of other things. So you might consider in the future using this kind of generator iterator style. We will see what comes up, but up until now, building libraries like that or building functions like that would be pretty error prone, because everything would have to rely on code generation or the MT interface. But now with generic types, such things become possible. Okay, oh sorry, wrong direction. Yeah, you've seen that one. Nice, very good. Let's take a look at the time. time flies. We are already at 4:45, so I'm at the end of the time and I'm at the end of my slide deck. So I think we should take a look in the chat and see how people liked it and whether there are any questions. Let's see.